Well, first of all, why do we need to find the area under a graph? Let's imagine that you are going on a ride in your brand new cruise bike. On your dashboard, the odometer is broken and only speedometer is working fine. Now you want to know how far you traveled based on the information from instantaneous speed alone. And of course, you can keep track of your time. How can you achieve such challenge? Let me help you. First, plot your information on a piece of graph paper. Now, the x-axis represents time and y-axis represents your instantaneous speed. If you were traveling in an uniform speed, you can just find the distance you traveled by multiplying the constant speed with the time you traveled, which means the area under this graph. Now, it's highly unlikely that you are moving on a uniform speed, and your graph may look somewhat irregular like this. With the same concept as before, how can you find the area under the curve? On a very basic approach, what you can do is bring the curve on some grid. Here, one interval on x-axis represents a second and one interval on y-axis represents 1 meter per second. Now the area of each square on the grid is exactly 1 meter. So by counting the number of squares that are more than 50% filled, just by eyeballing you can estimate the distance you traveled. Well, this method works, but it is tedious and nowhere near the mathematical elegance we are about to uncover. Another better approach would be breaking down the time you travel into equal intervals, let's say n intervals, and forming rectangles that closely resemble the original shape of the curve. Finding the area of rectangles and adding the rectangles is no rocket science. But the problem still is, how do we know the exact dimension of each rectangles? Now suppose there is a function that tells us the speed of the bike at any given time. In other words, f of t represents the speed of the bike at time t. The time interval from a to b is split into 4 smaller intervals.